Hello, my name is Brooke Boger, and my honors option presentation will be about soaps and detergents. Soap is an everyday household item that most people don't think much about, but soap is truly an amazing creation that deserves so much more credit than it is given. Without soap, our lives would be completely different. That grease stain on your favorite pair of pants would be stuck there forever. The old food on the dishes you eat off of would be nearly impossible to get off. Soap does this amazing thing where it surrounds the dirt or food or grease and it picks it up and allows it to be washed away. But what allows soap to do this job? In this presentation, I'm going to explore soap and the properties that give it its function. I will also discuss soap's counterpart, detergent, and why it is sometimes more useful than soap. Soap is made up of many long molecules called hydrocarbons, and on one end of these hydrocarbons is a carboxylate group. What does this mean? This means that one end of the soap molecule is attracted to fats and oils. This is the hydrocarbon end, and the other is attracted to water. This is the carboxylate end. The hydrocarbon end is attracted to fats because it is made of methyl groups which are nonpolar. The fats and oils are also nonpolar, therefore they attract. The other end of the soap molecule is attracted to water. This is the carboxylate group. The carboxylate contains two oxygens, one that has a negative charge. The oxygens gives the side of the molecule polar qualities, and the charge gives it its ionic properties. Being polar, the carboxylate is attracted to other polar things, in this case water. A soap molecule is very unique, having both a hydrophobic and hydrophilic side. Therefore, soap is considered to be an amphipathic molecule. Having this property gives soap its function. You've probably heard that soap forms a micelle around oil particles just because of the hydrophobic and hydrophilic interactions. While that's not entirely wrong, it is also not entirely true. Micelles do in fact form, but it is not just due to the amphipathic nature of the soap. Because oils, grease, and soap are hydrocarbons, when they are dispersed in water, the water molecules rearrange to maximize the number of hydrogen bonds that make one another. They form a cage-like structure around each hydrocarbon molecule. This is the micelle. The cage of water molecules around each hydrocarbon molecule is a more ordered arrangement than what is found in pure water. This more ordered arrangement results in a decrease in entropy. However, when this happens, the oil molecules clump together, creating a very large micelle and decreasing the amount of ordered water, and therefore increasing the entropy. The increase in entropy is energetically favorable, so the water will work to decrease oil and water interactions by clumping soap and oil into micelles. And this is how soap is great at washing away dirt. Fun fact, the reason soapy solutions look cloudy is because of the micelle being large enough to scatter the light. You might be asking, how is soap made? The answer is through the reaction called saponification, which happens in an industrial setting. Saponification begins with a triglyceride, which is found in fats and oils and is reacted with 3 molecules of sodium hydroxide to yield a glycerol and 3 molecules of soap. Essentially, what this reaction does is cleave the triglyceride back into a carboxylate, which is the soap, and an alcohol, the glycerol. This is done through a nucleophilic attack at the carbonyl group by the hydroxide, which will then kick off the leaving group through a tetrahedral intermediate. The carboxylate end is then deprotonated, giving it the negative charge. The process of saponification is a relatively easy one to perform, and people often make their own soaps in their homes. All you need is a good oil, I recommend coconut, sodium hydroxide, which is known as lye, heat, and time, as this process can take 24 to 48 hours. Although soap is a good cleaning agent, its effectiveness is reduced when used in hard water. Hardness in water is caused by the presence of mineral salts, mostly those of calcium and magnesium, but sometimes also iron and manganese. The mineral salts react with soap to form an insoluble precipitate known as soap film or scum. The reason that the scum is insoluble is because of the 2 very long hydrophobic chains from the soap molecule being attached to the calcium or the magnesium. These long chains prevent any water from interacting hydrophilically with the charged end of the molecule and therefore make it insoluble. Calcium and magnesium are the most common to form soap scum because they have a +2 charge, so therefore they can bind with 2 soap molecules, while the typical sodium salt only binds with 1 soap molecule, making it more soluble in water. Soap film does not rinse away easily. It tends to remain behind and produce visible deposits on clothing and make fabrics feel stiff. In hard water, soap is often used up by reacting with hard water minerals to form the film. This reduces the amount of soap available for cleaning. Therefore, you will not get a good soap lather in hard water. Soap molecules are not very versatile and cannot be adapted to today's variety of fibers, washing temperatures, and water conditions. This is where detergents come into play. A detergent is an effective cleaning product because it contains one or more surfactants. Because of their chemical makeup, the surfactants used in detergents can be engineered to perform well under a variety of conditions. Such surfactants are less sensitive than soap to the hardness minerals in water, and most will not form a film. Surfactants are very similar to soap and act quite the same with the hydrophobic end and the hydrophilic end. There are many types of surfactants. Anionic, which have a charge and act the same way as soap. In fact, soap is considered an anionic surfactant. An example of an anionic surfactant is given above, showing a negative charge on the sulfur. There are non-ionic surfactants. These do not carry a charge, therefore they do not interact with the calcium and magnesium ions in hard water, which do carry charges. The non-ionic surfactants are extremely useful and are the reason that detergents can work so well in hard water. An example of a non-ionic surfactant is given above, with multiple oxygens that all have two lone pairs, leaving the molecule a neutral. And there are cationic surfactants, which have a positive charge. An example above is the molecule with a nitrogen that has no lone pairs and therefore has a positive charge. Overall, we have explored the wonders of soap. We have looked at their structures and how that gives them their function, what reactions will create soaps and detergents, and how detergents are sometimes the better choice over soaps. Soaps and detergents are extremely useful in our daily lives. We would not be able to live the way we do if they did not exist. I hope that after learning about the wonders of soap, you too will be able to appreciate them even just a little bit more. Thank you.